So I'm going to walk through two simple problems just so that we can model. So we're set up for next week because in class we've been doing kind of theoretical concerns, and I just want to talk through problem-solving concerns. So let's just quickly bring everything together. From chapter 7, work net is equal to delta KE, right? So I'm sorry, that is my 513 notation, excuse me. So we're using sigma W is equal to delta KE, right? So that we know, add up all the works between 2 points in space, that's equal to the change in kinetic energy of the object between those 2 points. Fair enough. And hopefully what we have figured out here is that the work done by a conservative force is the negative change in the potential energy associated with that conservative force, and that the work done by non-conservative forces is equal to the total change in energy, right? That's the new stuff from recent. And along those lines, we know that the total energy of a system is equal, total mechanical energy is just the sum of the kinetic energies plus the sum of the potential energies, okay? And the last thing that we said is that the potential energy due to gravity is mgy, right? So how do we use these equations? We're going to add some more as we go along, potential energies, but this is fine for now. To do problems, let's look at two very simple problems. One in which there are no non-conservative forces doing work, and one in which there are. So we're going to look at problem chapter 8, problem 13, and then 33. So 13, this should be a problem that you're familiar with from last year. I have this like little slide doohickey here, and a marble that's going to be moving down that slide. We're told the height of a couple of points. Now here, they name points, and so we're going to use that nomenclature there, A, B, and C. They give us the height of position A, or that's 5 meters above the ground. That is 3.2 meters above the ground, and this is 2 meters above the ground. And it says if this particle, which has a mass of 5 kilograms, is released from rest at position A, so then we know the speed at position A is 0, find the speed at B and C, and then find the work done by gravity going from A to C. So let's go through this. So if I'm trying to set this up, the problem actually does a lot of the setup for us. So a couple of things that I want to say. First, we're going to draw a picture. There is no energy and work problem where you want to function without a picture. You absolutely need a picture. The second thing we're going to do here is we want to define where all of our potential energies are equal to 0. Right? So in this case, I want to find where my gravitational potential energy is going to equal to 0, right? So we know the equation mgy, y is a position variable. That means I need to set a y is equal to 0 or a ug is equal to 0 line. Now, I could go with their standard here, and I could put the ug is equal to 0 line here, right? But I could actually also put the ug is equal to 0 line here if I wanted to. There's nothing that says I have to put it at any given position. But because of the way this problem is phrased, I'm just going to put my ug is equal to 0 line here. So that's going to be an important part of the problem. If there are other potential energies, you have to define where their 0 points are as well. As we'll talk about next week, for some potential energy functions, you're going to be able to pick wherever you want for where the potential energy is equal to 0, and for some you can't. Now, with gravity, what does that mean? Any position above this line has a positive y, any position below this line has a negative y. No big deal there. So step 1, draw the picture. Step 2, set your potential energy equal to 0. Step 3 is actually going to be to demarcate where the important points in the problem are. Now, this problem does it nicely for us. It gave us A, B, and C. In some problems, they don't tell you the important points. I'm going to ask you to label the important points. Why? Well, when approaching this now, what do we want to do? Well, what we want to do is sort of think about total energy at each of these points. Now, this is an optional step. I just think it's a very helpful step. If I think about the total energy at position A, that's going to be composed of just the gravitational potential energy at position A, right? There's no kinetic energy, it's not moving. At B, the total energy at position B is going to be composed of the gravitational potential energy at B plus the kinetic energy at position B. And at C, it's going to be composed of those two flavors of energy as well, right? But the values are not going to be the same because the gravitational potential energy is different, and therefore we'll find out the kinetic energy is different, right? So thinking about total energy at different spots, really important. And then what we want to do is think about linking the points. So two things to think about. I know from what we said before that the work done by non-conservative forces is equal to the total change in energy. So there's two things I want to think about. If the work done by non-conservative forces is zero between 2 points, what that means is that the energy, total energy of the system, is the same between those 2 points. But if W and C is not equal to zero between those 2 points, the final point minus the initial point is going to equal the work done by those non-conservative forces. And so we always want to think about, between the 2 points that matter, are there non-conservative forces doing work, right? So between A and B, what forces are present? Well, I've got gravity, which is a conservative force, and I've got the normal force, which is a non-conservative force. But here's the thing, between A and B, the normal force is not doing work. It exists, but it's not doing work because, as we discussed, at any given point, the normal force is going to be instantaneously perpendicular to the displacement, the small little displacement vector at that point, because we know the displacement vector is going to be tangent to the path, and the normal force is perpendicular to that tangent. So between A, B, and C, there are no non-conservative forces doing work. Therefore, finding the speed at position B is relatively simple in this problem. I can say the work, or the total energy at A, is equal to the total energy at B because the work done by non-conservative forces between those 2 points is zero. That's my premise. And so what do I do from there? I don't know why I'm writing in red. Let me go back to blue. I can say that the potential energy at A is equal to the potential energy at B plus the kinetic energy at B. And now I can just plug in, because I know this is mgy at A is equal to mgy at B plus 1/2 mv at B at squared. Now, I could cancel out the m's, but I'm going to tell you, in some problems, even though you can, it's not useful. In this particular problem, we can actually save ourselves some work if we don't cancel out the m's. Let me show you why. Because let me do my plug-in here. So our plug-in here is 5 kg, 9.8 newtons per kg. YA is a positive 5 meters, is equal to 5 kg, 9.8 newtons per kilogram, 3.2 meters plus 1/2 5 kg v at b squared. Okay, and so let me just grab my calculator and find some numbers for me. Boom, right? So this number is 245. Notice I'm doing some internal calculations here. Why? In longer problems, what you're going to find is oftentimes you're going to be able to steal work from different lines if you've done some internal work. So right here, I can now just go straight to what VB is, okay? Because I've done the internal work I need to. That's going to make later parts of the problem a little bit easier. Okay, and square root. Okay, I got plus or minus. I'm looking for a speed, reject the minus, 5.4 meters per second. There we go. So now when I'm going down to, say, position C, I know that between position A and position C, still there's no non-conservative work being done, so there we go. But notice here, because of the fact that I didn't cancel out the mass, this number here is the total energy of the system at that point, and I can just steal that number right down here, right? But if I canceled out the mass, the number that would be here would not be the total energy of the system at that position, so that's kind of really nice. So this just becomes the potential energy position C plus the kinetic energy position C. So 245 is equal to mgy at C plus 1/2 mv at C squared. 245 equals 5 kg, 9.8 newtons per kilogram times 2 meters plus 1/2 what's m here? M is 5 kilograms. VC it squared. I'm just going to find some internal numbers because they might make my life easier in a minute. 0.5 VC it squared. VC is equal to 245 minus 98 divided by 2.5, square root of quantity, 7.67 meters per second, which makes sense that it is faster because it is lower down. More of the potential energy has been transformed into kinetic energy by the work done by gravity. So let's do the B part. It's asking what's the work done by gravity between points A to C. Oh, well, the work done by gravity is the negative change in the potential energy due to gravity between those 2 points. So the work done by gravity is equal to negative final, which is C minus potential energy at A. And because I've done my little side work here, folks, I can steal. The potential energy at position C is 98 joules. The potential energy at position A was 245 joules. And there we go. I can find out what that answer is because I looked ahead and I knew that it would be really nice to have those internal numbers, which is often true when you have, so it's 147 joules, multiple parts in a problem. So just because you can cancel things out doesn't mean you ought to cancel things out. So there we go. So now let's look at problem 33. So 33, we have very simply a box that is initially moving up a hill. And we know it's going to come to rest at some point after traveling a certain distance up the hill. So it's going to come to rest after traveling 3 meters up the hill. So let's approach this problem in the appropriate way. We can do this problem using work energy theorem, but I wanted to use this using the chapter 8 methodology. So here's what it looks like in chapter 8. Same thing as before, we have a picture. We're going to declare where potential energy is equal to 0. I'm going to make that wherever my box is initially. So I'm making this my UG is equal to 0 line, okay? Then I'm going to label the important points. The first point I care about is the position it starts. The second point I care about is where it comes to rest. That gives us that the speed at position B is equal to 0. The next thing I'm going to do is I'm going to write total energy statements. The total energy at A is just equal to the kinetic energy at position A because it's at the UG is equal to 0 line. And at B, all I have is the potential energy due to gravity at position B. Position B is defined by the place where it comes to rest. So there it goes. Then I ask myself, between points A and B, is energy conserved? And what I notice here is that no, it's not, because there is friction in this problem. Okay, so what I want to find out then is, because like the end goal here is what the coefficient of friction of this thing is. So it kind of walks you through a couple of steps. So I'm going to say here, my premise then is the work done by non-conservative forces between B and A is equal to the change in energy between those 2 points. So here, what forces are non-conservative? Well, the normal force is non-conservative and the frictional force is non-conservative. And so that's going to equal the total energy at B minus the total energy at A. I know the work done by the normal force is 0, theta normal is equal to 90. I can put in place what I know about the frictional force. That's going to be Fk. What is that displacement between B and A? Cosine of the angle is equal to, this becomes the gravitational potential energy at B minus the kinetic energy at position A, right? So here, because I've got this frictional thing, I do need to do a force problem. So I'm going to come up here and do the very quick force problem, right? Because I'm going to need components. Theta. So we're going to go sigma Fy equals MAY. We'll say off the incline is positive. Fn minus Fgy is equal to MAY. That goes to 0. Fn is equal to mg cosine of whatever this angle is, right? I probably should say this is theta k. So then what do I have? So this is the coefficient of kinetic friction times mg cosine of the angle of inclination. I know what the displacement between B and A is. It's given in the problem. Cosine of 180 is equal to mgy at position B minus 1/2 mv at A squared. So what do I know here? I know m, I know g, I know this angle theta, that is 30 degrees. I know that this is 30 meters, that is 180. I know that. I know that. Y at B. Okay, so now I need to actually look at this, right? Because we're actually told that this is 3 meters, that's theta. So YB is going to be that side of the triangle. So sine of 30 degrees here is equal to YB over 3 meters. So I have that as well. So the end goal here is the coefficient of kinetic friction. So the coefficient of kinetic friction is equal to 5 kilograms. Just go this. I'm kind of skipping to the end of the problem. They give like an A, B, C, but all of this is just in service of trying to get to this final result here, right? So I'm just kind of skipping to the end, to the part of the problem that actually matters. So M is 5 kilograms, 9.8 newtons per kilogram. This is 3 meters sine 30 minus 1/2 5 kilograms times VA. It's initially traveling at 8 meters per second quantity squared, right? And so from here, it's just throw all the things into your calculator. 5 times 9.8 times 30 cosine times 3 times 180 cosine, okay? And so this is negative 127.3 mu, just to do a little internal work because I have my bad calculator here. 73.5 minus, okay, 160. And when you do that, then you get that it is equal to 0.68, and there you have it. We can go back and do all the other pieces if you'd so like, but that is the final answer from that problem. So if we're good to go back and do those pieces, what's the change in the object's kinetic energy? So delta KE between those, that's just going to be 0 minus whatever that 160 is, because I can steal that number. So the change in kinetic energy is negative 160 joules. The B part of that was the change in potential energy. So delta U, U final minus U initial, or U at B minus U at A. We know that that's 0. And so that's just the MGY thing. That's our 73.5 joules, to steal that from there. And what is the next part, the frictional force? Yeah, I mean, I actually don't particularly care about what the frictional force is, but we could calculate it now because I could do 0.68 times mg cosine of 30. So 5 kilogram, 9.8 newtons per kilogram cosine of 30, in case you did it the sort of piecemeal way, right? But last year, the way that you would have done that is by kind of building it up in the way this problem asks, whereas this year, what we want to do is be developing our premise statement from the idea of work non-conservative force is equal to the total change in energy. Energy is not conserved, and what is the implication from there all the way through to the problem. This is a much more sophisticated analysis. It's a much more holistic analysis, right? So what is Chapter 8? Chapter 8 largely is going to be the calculus stuff surrounding potential energies we talked about, and we're going to continue to talk about. It is conservation of energy problems, where, as we saw here, energy is conserved in the problem, then energy is not conserved in the problem, and then sometimes a mix. What happens if I have no friction from here to here, but then there's friction here? I might have between A and C, energy is conserved such that EA is equal to EB or EC because work non-conserved is 0. But then in the next segment of the problem from, say, C to D, the premise is the work done by non-conservative forces from C to D is the total change in energy from C to D, or ED minus EC, right? And so it's a blending of those two things. Then, once we got that, we're going to start to bring in all the old stuff because we're going to see how we can do conservation of energy with projectile motion, how we can do conservation of energy with systems problems, how we can do conservation of energy with circular motion problems. So it all starts to gel together.